I'd like to start by land acknowledgement. I acknowledge that Canada, coast to coast, is land of First Nations and other Indigenous groups, and I'm very grateful to have the opportunity to work on this land. Hello, everyone. My name is Madeh Piryonesi, and today I'll be talking about the application of data analysis to asset management with emphasis on roads. So I have a PhD in this topic, and I know a thing or two, and I'd like to share them with you today. And this video is recorded for Professor Tamil Diravi's class in University of Toronto. All right, so this figure is quite famous. It's called CRISP, and I want to re-emphasize its importance and say that all data analysis efforts are sort of following this figure. So in the first step, it's very important to understand what business problem are you after, what problem do you want to solve, and understand the type of data that you're working with. As you see, the role of data is very central. So I cannot emphasize this enough. You should know the type of data that you're working with, the relationship between your data, the data structure, and all of that. Preparation and cleaning of the data, it's very time taking, often time takes like the majority of time and effort in a data analysis project. And so this is very important too. Then you get to fit models and learn models based on your data and evaluate your models, see if they are any good or not, and then implement your models. So I'll try to talk sort of about almost all of this in this lecture and use a real world example, the example of roads in North America, and share some of my experiences about these. So I'm not going to teach you SQL or Python or RapidMiner or any of that or Excel, but I want to talk about my project and say how each of these tools helped me and show a few examples, really hands-on examples of each of these stages. So the problem that I'll be talking about is the deterioration of roads, and I trained machine learning algorithms to predict their deterioration. I looked into two performance indicators, pavement condition index and international roughness index. The first is known as PCI, the second is known as IRI. And I'll be mostly talking about the first one because we learned that around 85% of municipalities in Ontario are using PCI. So if you're not familiar with these performance indicators, PCI and IRI, it's fine. So basically PCI, I'll be talking about it later, but to give you a short overview, it's a measure of how many distresses are on the road surface. So if you, for example, so it's a number between 0 and 100. If your road is terrible, 0. If your road is great, 100. And for example, if you have a pothole, your PCI will fall into 80, right? If you have one small crack, your PCI will fall into 95. And on the other hand, IRI is a measure of roughness, how rough your road is. If your road is pretty smooth, you'll have a small IRI. Otherwise, the IRI is going to grow over time. So the thing that was sort of unique about my work was I used data that is very affordable to municipalities after talking to them. And I trained a variety of different algorithms, made some comparisons, and I looked into the impact of climate change as well because the predictors that I have, they were very much could reflect the impact of climate change, basically. So this slide isn't bad. It's showing the sort of schematic picture of my models, especially for the classifiers. I did train regressions as well, but for classifiers, this is pretty helpful, I'd say. So what I wanted to see was, assuming that I have my initial condition of my roads. For example, I know that my road is in a good condition today or in a bad condition today. Assuming that I know this, and I have a set of other features such as precipitation, freeze index, maintenance history, traffic, age of roads, and things like that, can I train models to predict the future PCI class, whether my PCI is going to be good or satisfactory or bad or what? So as I said, PCI varies between 0 and 100, and this is a classification proposed by ASTM. So this is good, and it goes down all the way to failed PCI. So this is what I'll be talking about today. And I trained a range of different algorithms: decision trees, random forest, gradient boosted trees, KNN, regression, logistic regression, linear regression, random forest regression, and all of that. And I'll talk about a few of them and some of their differences in this presentation. But I try to also show you some of the like really unseen parts of the iceberg, data preparation and data cleaning and that kind of stuff that I did using SQL and Excel and other tools. Okay, this slide is showing a big picture of what I was doing. So the resources that I used was, one of them was this wonderful database called LTPP. It stands for Long-Term Pavement Performance. And I use other databases as well, for example, Roads in Ontario. But this database was at the core of my research, and it was very important. I will talk about that. I'll show you the website, and I'll do some data retrieval on it. So don't worry about it. I'll just pass at the moment. And then I got to read some 40 asset management plans in Ontario to learn how people are doing infrastructure asset management. I talked to experts, obviously, and I read these standards that already exist in the field. The main tasks were very similar to other data analysis efforts. So I had to first collect data and retrieve it from the sources that exist out there, the operational sources, right? And again, I'll show you examples of how I did this. And then and then I had to do a lot of data preparation and cleaning. I wouldn't bother showing you each and everything, but just to show you a few examples of how I prepared the data and how time-taking and laborious data preparation is, I will show you a few examples. In most data analysis experiences that I had, data preparation and cleaning is really taking most of your time. It's like 80%, maybe 90% of your work. So it's quite important. So it's important to know how to work with data. And then model training and evaluating the model was the next stage, and eventually implementing it in a usable form. So what I have in mind is I'll go through my slides, present what I did in a sort of high-level manner, and then when I finish my presentation, my slides, I would go to my database and show you how to query data or how to clean data and how to train models and so on. So stay tuned. So I said preparing the data is very important. The PCI that I talked about, as I said, it's basically a manifestation of how many districts are on the road. But the thing is, the standard that this PCI was calculated based on is ASTM, and their curves are very grotesque and old, and their formula wasn't there. So just to be clear, the right one is the ASTM curve, not this one. But the formula isn't there, and I had to digitize all these curves and find the formula for PCI. So that was a big part of the effort for data preparation. This slide is pretty good to give you an idea of how PCI calculation works. So essentially, we have to collect different types of distresses on the road. For example, alligator crack, bleeding, edge cracking, potholes, and there is like 10 other at least distresses on in the ASTM guideline. And then when we collect all the distresses, we turn the distress density into something called dedoc value to account for the impact of different distresses happening at the same time. So ASTM has a set of curves. As I said, their formula is not given, so I had to sort of digitize all the curves and fit a formula to them and find their function. So here's, for example, a formula for pothole. If I'm not mistaken, this is for medium severity type of pothole. And later on, you have to use another set of curve, which is called corrected dedoc value. I had to again find the formula for all of them. So after digitizing the curves and fitting these formula, I had the formula for PCI calculation. And so here is, for example, some of the formula. And then I had to develop a program to calculate the PCI because I was working with a large amount of data, thousands of examples of roads, so I couldn't go and calculate each of the PCI values manually, right? So I use this. So this is a flowchart that I prepared for this PCI calculation based on ASTM. It's actually the other way. I rotated it to make it fit the page. But as you can see, as you can appreciate here, it has a loop that is representing a repetitive process in which PCI is calculated. So all of this was before me starting doing any real analysis on the data. I had to prepare the data and put it into the right format. Because the database that I was working with, it had all the distresses that I talked about, but it didn't have PCI. And we in Ontario were interested in this PCI thing. Okay, so after doing all of that, let's get to the analysis part a little bit. My analysis had a few facets. One of them was the comparison of algorithms. We have different type of algorithms in the literature. Generative, discriminative, lazy learning. These are all type of algorithms. Here are examples of them. And what predicts what better? I think that matters. So that's what I focused on partially. And then data size. What is the impact of data size? How using a larger training set can improve the quality of our algorithms. Informativeness. Which algorithm, which feature or which predictor is more informative and contributes to the prediction better, and segmenting the data, which was sort of the last part of my analysis, was basically based on the fact that the data was pretty broad and geographically very diverse. And I thought if I segmented into smaller and more meaningful subsets, better correlations and higher accuracies could be found, which was true. For example, we learned models for different climatic regions, for roads with different maintenance history and different functional classes and different intervals of prediction. And each model resulted in a higher accuracy. And of course, other than all of this, I did some analysis on climate change as well, which is beyond today's topic. This slide is pretty helpful as well, communicating what I just said. So the database, as I said, it was called Long-Term Pavement Performance, LTPP. We used some 15 attributes to predict PCI and IRI. Of course, we use subsets of these 15 attributes as well. For example, models trained only using 2, only using 5, because they are not equally informative. And the municipalities who are going to use these analyses, they have different data availability, right? And for PCI, more than 3,000 records were used. For IRI, around 30,000 records. Of course, data cleaning and preparation was a big part of the the project, especially automating PCI calculation that I did talk about, removing erroneous examples, and some of the examples included missing data as well. So either removing or filling in those missing data was a part of the project as well. And collating and putting different fields and different tables together, this was very important as well. I'll talk about all of this hopefully in the next few minutes. And feature selection. So what features do we choose for our analysis? This was important as well. So the main considerations that we had were really around cost of the data and availability of data, and whether they are relevant to climate change. So essentially in data analysis, um, this is a very important issue, whether you have the data in there or not. And a lot of times this data could be very costly, so acquiring the data could take a lot of time and financial resources. That's why we prefer to stay with data that is affordable. And I mentioned climate change. I think it's important to mention this here as well. The reason that we use this very broad data set was to um, incorporate the impact of climate change on roads, because this data is very geographically broad, and we know that by the almost end of the century, by 2080, for example, or 2100s, our cities are going to be looking very different. For example, this is a study conducted by several scientists, Fitzgerald and et al., showing that by 2080, Montreal is going to look like New York City in terms of climate, or Toronto is going to look like this location here, or New York City itself is going to be hotter and drier, for example. It looks like somewhere down there. So knowing that, it was important to have a data set large enough to be able to capture this variability. So let's get to the type of models that we learned as well. We talked about municipalities needing deterioration models, and the models that they were using were mostly based on one attribute, and that was age. So the model on the left here, right? And they were mostly using deterministic models that cannot entertain probability. So these models are pretty simple and useful, but they have some limitations. For example, if you look at this model here, you can see that it's predicting PCI based on age, and it's saying when your road ages, your road becomes worse, right? So that's pretty obvious. But the issue is, for example, if you compare these two states, Arizona and Utah, so Utah and Florida, Utah is much colder than Arizona, and Florida, the red one, is much more humid than Arizona, right? So you expect the curve for Arizona to be above these curves, but in this case it's below, and it's almost like 10, 20 units in all cases, lower than the other two counterparts. So the reason for this, when we looked into the data, was their traffic. The roads in Arizona, for example, had a larger traffic and also a larger number of trucks going on their roads, passing on their roads. So that's another issue of these type of models, that they cannot take into account all these variabilities and all these sources of deterioration. On the other hand, here's a very simple type of model that we trained. It's called a decision tree. You probably have seen it. It's very popular because you can visually represent it using this graph. And as you can see, we can have different type of attributes on it. For example, initial PCI, age, precipitation, freeze index. So the model could tell you depending on how old your road is, or what does your climate look like, or how, like, what the annual temperature is. Your road might end up being in a good condition or in a satisfactory condition or fair, and so on. So this is the beauty of this type of model. And also, these leaves down there, they are not one deterministic value. They could be probabilistic. So the model could tell you this road will end up being fair with a probability of 50% or 80%. And this is very useful for risk analysis and risk assessment. So speaking of simplicity, this model, as I said, is very simple and very popular. It also has problems. One of the most important problems being that its accuracy is not the highest, and also another problem is its robustness. It's not always the most robust type of algorithm. That's why we develop a another set of algorithm when we work with decision trees and tree-based models. They are called gradient boosted trees and random forest. So gradient boosted trees is an example of a boosting algorithm, and the random forest is an example of a bagging philosophy. So very briefly, this is how gradient boosting works. And boosting, as the name suggests, it's a way of boosting the accuracy of an algorithm. And essentially, you could learn any type of boosting algorithm based on what your base learner is. For example, if your base learner is a tree, you would learn a gradient boosted trees, right? But you can put inside this function of boosting, or this machine of boosting, you could put a neural net in it. You could put whatever you want in it, right? But this specific case is very famous because it's using decision tree, and it's called gradient boosted trees. So how does it work? So the way it works is this algorithm first divides the data randomly into a bunch of subsets. For example, in this case, just for the sake of representation, I divided the data into five subsets, but in reality, it could be much more. For example, 500. Okay, and then it learns a tree based on each of these subsets, right? So tree 1 corresponds to subset 1, tree 2 corresponds to subset 2, and so on. And for any incoming new example, for example, this example, this is a road, say in Texas, for example. It has an initial PCI of 86, and these are the other values. So when our model, our gradient boosted trees model, wants to predict, each individual model or each base learner will make a prediction. For example, this one makes this prediction. It's predicting that this road is going to be in a fair condition 3 years from now. Tree 2 makes this prediction. Tree 3 makes this prediction. The way we finalize the prediction and sort of aggregate all these results is by, in some cases, by taking a majority vote, and in some cases by using a panel of experts. So the majority vote, if we take a majority vote here, we have 3 trees predicting fair, 1 predicting good, 1 predicting satisfactory. So we go with majority vote, it's fair, right? So this is an example of bagging in the case of trees random forest, right? But the problem with majority vote is sometimes some of these subsets are very small, and the algorithm trained based on them is very inaccurate. For example, if you look at decision tree number 6, it's barely a tree. It's just one leaf saying that no matter what your input is, your road is going to be in a fair condition. So this is really a very bad type of prediction, as you can see. It's even worse than a random type of prediction because it's not sensitive to data at all, right? That's why in boosting, we go one step further, and instead of a majority vote, we create a panel of experts, and instead of just taking everyone's vote as it is, we assign a vote to the tree. So essentially, the models are not just equal individuals, they're like experts. The ones that are more accurate, their vote is going to be magnified, and vice versa for the less accurate models. So this was about tree-based models. And as you can see here, um, you can see that here I have two things to show. On the right, you see the impact of um, having a gradient boosted trees, which is more accurate than a single tree. So this green dot here shows a single tree, one decision tree. And the red one is showing a gradient boosted trees. And by adding more base learners or more trees, you can see that the accuracy is increasing. And it goes from 72 to almost 83, right? So the more trees you have, the more accurate your algorithm is. But always you have to be, of course, aware of and vigilant of overfitting. On the left, what I have is the impact of data size on accuracy. So here we have accuracy of a decision tree, single decision tree, and the number of data points that are used to train this tree. And as you can see, by adding more data, the accuracy of the tree increased, right? So the more data, the more accurate our models are. So I talked about decision trees. I'll quickly talk about 2-3 types of other algorithms, and then I'll get into the hands-on part about data cleaning and model training and so on. This one there's another type of algorithm called naive-Bayes classifier. It's very popular because it's very simple and computationally it's very cheap. So it's very popular. It also, but the problem with this one is it has a little bit of a problem of low accuracy in some cases, but still very popular because, for example, when you have in cases that you have a very large number of dimensions, for example, text analysis, these computationally available algorithms could help a lot because you could run them in the twinkle of an eye, right? But again, their accuracy sometimes could be a problem. That's why we could boost this and fortify this algorithm using a philosophy called density estimation, or an approach called density estimation. And for example, in this case, so let me first quickly say how does naive-Bayes works. So as you remember, naive-Bayes classifier works based on Bayes rule, and this is Bayes rule. And this algorithm is called naive because it's assuming that the features are independent and you can just multiply the intersect of their probability, right? But the issue with naive Bayes is it's always assuming that this probability of x given y, it's always normally distributed if your variable is continuous. So this could be a problem. A lot of times the variables, real world variables, are not normally distributed. That's why what kernel density estimation is doing is it's fitting a better distribution to these probabilities, and if we have better distribution for this, we can increase the accuracy of our model. And as you can see here, by adding more kernels in the case of my Bayes classifier, theoretically the accuracy could increase to 90%. So that's what I meant by fitting normal distributions. Here in my case, because I had 5 classes of PCI, good, poor, satisfactory, and so on, those conditional probabilities will be 5 distributions, and my naive Bayes is naively thinking that they are all normally distributed, but a lot of times it's not the case. That's why we use this density estimation, and in this case you can see that I used 3 kernels and the distribution that I got is really far from that unimodal distribution. As you can see here, we have 2 three modes actually in our distribution. This one is a little bit more like normal maybe, but these four other classes, they are very different. And this is kind of close to reality because this is the real distribution of our data. And as you can see, it's not very much, maybe not normal, and it's sort of multimodal, and it's not unimodal. Also, this I mean, you could also see that this distribution is a bit more realistic because if we were to use the original normal distribution, you can see that for this specific feature, for example, freeze thaw, number of freeze thaw, we are getting negative values on this side of the curve, right? Which is not realistic because like freeze thaw, number of freeze thaw cycles is a number between 0 and 365 number of days in a year. So as you can see again, this new distribution is a bit more realistic, and this is what giving us the higher accuracy. For example, in this case, I used 3 kernels, and the accuracy increased from 50% to 71%. So this is a way of increasing your accuracy using this approach. And as you can see, by theoretically adding more kernels, the accuracy did increase up to 90%. And this is a cross-validation type of accuracy, so it's not the training data itself. Another very common type of model is KNN, K nearest neighbors. Very common because its philosophy is pretty simple. It's an example of lazy learning. In this slide, I just wanted to say that some of these algorithms, for example, KNN, or some of the clustering algorithms, because they are based on a measure called distance or Euclidean distance sometimes, they are sensitive to dimension of data. They are sensitive to how different the dimension of your data is. For example, you could have a data about traffic, which varies between 0 and 35,000, right? And you could have data of freeze thaw that varies between 0 and 150, right? So 35,000 and 100, they are very different. At the same time, you could have IRI that varies between 0 and 5.6, right? So in those cases, normalization could help a lot. And as you can see, after I normalize my data, you can see that in the blue curve, the data is normalized, and in the orange curve, the data is still not normal. And the blue curve is almost in all cases above the orange curve, showing that 10-15%, maybe more, increase in the accuracy of my data when my algorithm, my data is normally distributed. Sorry, it's normalized. So I guess I'm getting a little bit tired. So what I do is I give myself a break. You guys can take a break or just sit in class. It's up to you. But in the next session, in the rest of my presentation, what I do is I will show you a few examples of SQL queries, preparing the data, training models, what does my data look like, how did I prepare it, and things like that. So I'll make this part a bit more hands-on. Hopefully that makes the class a bit more interesting. Okay. All right, so what I had in mind in this part of the presentation was to uh, use a few of the tools that I was talking about and show you a few examples of how they work and what they are used for. So I thought it makes a lot of sense to just go to the LTPP database that I talked about. So here's the URL infopave.fhwa dot gov. That's funny, gov. So this is their database. It's pretty very well maintained, and it's a clean data. And to give you an idea of how broad the data is, you could see that it's really spanning all over the United States and Canada in some cases. So they have these sections, Alberta, these in Ontario, mostly southern Ontario, and quite a lot in the United States. And it has a nice interface, so you could go query your data probably using the interface. But the reality is the tool that I'm about to um, introduce, it's much more powerful, and it's what is called SQL. And if you go to this tab, to Data tab, and go down here to SQL export, this database gives you the option of retrieving the data using SQL. Okay, and SQL or SQL, some people call it SQL, some people call it SQL for historical reasons. And it's a pretty powerful tool, and you could use it. Gives you a lot of flexibility for retrieving data, for preparing data, and putting the data in the right format that you want. So hopefully the class is a little bit familiar with relational databases and tables and so on. But I can give you a very quick overview. When I talk about tables in a relational database, I'm talking about these things over here, right? So these are the tables that I have in my database. For example, this table, if I just drag it over here, has data about, these columns in a table are called feature. So for example, this one has data on state code, SHRPID, layer number, PMA, binder, and things like that. So it's mostly, as the name suggests, it's about asphalt concrete aggregate binder. It has that type of data. And for reasons related to efficiency, a lot of times these relational databases, they have tables that are normalized, as they say. So it has minimal amount of information to make its storation as efficient as possible. That's why, for example, this table is only, for example, about aggregate property for this type of road, right? And another table is only about, for example, general information of road. For example, this one in age, it has data about the date of construction of road, or when it was open to traffic, and things like that, right? So this is actually a good example to work with. So, and I'm going to show you a few queries generated by SQL. I think it's pretty useful. SQL is pretty simple to learn, but it's very powerful. So I encourage you to go online and take a look at their queries. I'll show you a few examples here. Hopefully they'll be useful. So if I want to retrieve a bunch of features or a bunch of data points in a table, I would say select. So let me zoom in a little bit. This is the keyword that we use for selecting data in a table. And if I say select star from a certain table that I just showed you, for example, in age, that would show me each and every data points in this table, right? So if I zoom out a little bit, that would be better. So here are the data points and the fields that I have in this table. So SHRPID is an ID for that road section. State code is the state that the road is located in. Construction number is a number that reflects the number of maintenances that are done on a road. For example, it varies between 1 and, for example, 10, right? It could be more even. Construction date is when the road is initially built. This is when it was initially open to traffic, and so on and so forth. So, and whether the traffic is going this way or the other way. So how do I know all of this? You should. This is about the part that I talked about, data and understanding. This database has a clean dictionary and also a manual. You can go read their manual, see what attributes corresponds to what. But again, Very important to understand the nature of the data that you are working with and to know where each piece of data is, right? So this is a type of query that I just show you. But if you want to be more precise with your query, you could, for example, go like select a specific attribute. For example, select state code from this thing where my state code equals to 87. 87, I already know it's Ontario, right? So here are the data of roads in Ontario in this certain table, right? So I would like to add another feature, for example, construction date. So the data of roads in Ontario in this certain table are one of them is built in 98, one of them is built in this date, right? So you could be as specific as you want. And here, as you can see, select is the keyword. These are the features that I want. Right, let me zoom in a little bit. And this is the name of my table. And after where you have that condition that you want to apply. For example, I said state code larger than 87. So let me show you an example or two, and then we'll go to data preparation, another example or two. So for example, here in my presentation, I did talk about all these types of distresses, right? Over there, like alligator cracking and pothole rotting and all of that, right? So let me show you an example of a query actually retrieving distress data. So to be able to retrieve distress data, first we have to know where the data is stored, right? So let's first go find the table the data is stored in it. So I believe, if I'm not mistaken, it's so let me go up. I think it's this table. Underline this underline AC underline ref. I believe this is the table with most distresses data. And if you want to take a look at the features in this table, you could see that it has quite a few features. Surveyor who surveyed the pavement, different type of crack, for example, alligator cracking, block cracking, and many more, right? Okay, let's. So I want to use the syntax that I just learned, right? So to show everything, the formula was select. Let me zoom in a little bit. Select star from this table, right? Select star from this table. So this would give us each and everything that is in this table, right? So let's zoom out a bit. Here is some of the information in there, and as you can see, the table contains 12,000, more than 12,000 examples, right? So it's a pretty large table, and you can see it has many states, and the survey date is over here. So the roads have been surveyed in 2004, 5, and way above that and beyond that. Construction number, as I said, it's the number of times the roads are maintained or a maintenance action has applied. This one has been rehabilitated twice, this one 7 times, right? And here are the type of some of the distresses that I talked about. For example, this is alligator cracking, right? And this is, so alligator cracking, low severity, alligator cracking, medium severity, and high severity, right? And over here you have longitudinal cracking, right? So let me zoom in a little bit. And other type of cracks that I talked about, see, and even more. We have patching, we have quite a few potholes, right? And this is, for example, the number of potholes that exist. Um, in most of these cases, it's 0. So these are the type of distresses. So let's make this query that I just talked about a little bit more specific, as I said. So I want to have the data on, for example, potholes. Okay, so pothole was called, the feature is called pothole. So this is pothole area and this is pothole number. So I'm interested in pothole number low severity, right? So I want to select pothole number and low severity from this table that I just talked about, where it is located in Ontario. So state code equals to 87. That would give me Ontario, right? So something went wrong. Let me zoom out a bit. Queries change. Let me select everything first. So select everything from this. So this would give me all distresses, as I said. But if I am interested in pothole number, potholes, it's potholes, sorry. So the name is potholes. There we go. An S was missing over there. Zoom in a bit more. There you go. So now if I run this query, what it would give me is the roads, the number of roads, the number of potholes on roads in Ontario, right? So you can see it's just a one column thing. This one has 1 pothole, the other has 0. So let's add a few other features, make it more readable. So state code, I add state code, I add SHRPID, these two define a road in this database, right? And I also would like to have survey date, right? I would like to see when this road was surveyed. If we have the data, let's see if we do. We actually do. So you can see that this certain road that was surveyed in 1990 had 1 pothole on it. The other few, they didn't. And if we go ahead, you can see that this road on 1990, this certain road had 3 potholes on it, this one too, right? So this is how you can make your data more specific. In the case of me training my PCI model, I was interested in the PCI in a certain year and a PCI in, say, 3 years later, right? So I had to retrieve the data of that certain that certain year, and then the year later. So you could make your query here, for example, more specific and say that I want the date. So I want the serve. So I already added one condition here, which is the state code is this, and I also can say the survey date be so, for example, smaller than this certain date. For example, if I'm interested in 2001, I would say smaller than December 31st, and this is just a little bit of syntax here showing how your year convention is, right? So let's see if this query works. Yeah, it did. So this one is returning all the surveys that were done before year 2001, right? So if I want to uh, make it really about year 2001 itself, I should say that my survey date would be larger than January 1st of 2001, right? So let's make this, right? So larger than this. Oops. Okay. So this would give you exactly the distances of the roads in that certain province, Ontario, in year 2001, right? So now assume that we have all of this and we run our model and like we run our PCI calculator and calculated the PCI. Now what I should do is, if I go back to my conceptual model over here, I have my initial PCI. Now I have PCI in another year because I calculated all the PCIs. Now I have to marry the two, make them, put them together so I can train models using that. So you could do that manually, but the problem is it's going to take forever. Uh, and instead, what I did, I used another tool, SQL-based tool. It's called Microsoft SQL Server. The reason I used that because of the way the data was encoded, but you could use open source tools or other type of tools that are available. So for example, I imported my data in here. For example, my PCI data in 2001, right? There you go. There is my PCI data for 2001. And I want to see how this data would, these roads would deteriorate in 2003, right? So I have also my PCI in 2003, 2 years later, for example. Apparently 2003 isn't here. So let me see if I don't have the data or it's just the way the name is. Okay. Maybe 2004, 3 years later. Okay, so this is PCI in 3 years later, right? So what I want to do is I want to put this PCI 2001 next to 2004 and make a prediction, right? Because right now they are separate, right? So I want to put them together. What I could do is I'm using this wonderful capability of SQL called view, and essentially what a view is, it's a temporary data format, right? So it doesn't exist on the memory. It's just a query that every time I run it, it goes to the memory and create it. So what I do is I'm going to use create a view using this type of command that is called inner join. So this is one of the very popular um, operations in SQL. Okay, joining tables. And the very quick overview of joining in SQL could be explained like this. For example, if you have two tables, table 1 and table 2, if you are interested in their intersect, you would write an inner join. If you are interested in table 1 plus those that both tables have in common, you would use a left join operation, right? So, and there are other types of joins. So in this case, I was interested in PCI in year 2001 and 2004, so I had to write an inner join. So if I run this query here, that would give me this, right? So that would give me PCI in year 2001 and PCI in year 2004. So right now I can make a comparison and train my model using this data. For example, in this case, it was PCI was 96, it deteriorated to 69, which is pretty large. And then you can name this view and use it. For example, I named this one Um, I think it's named PCI T01_04, I believe. Yes, so that's the name. Uh, so if I want to, for example, in this data set, I want to check for one of the most common issues in pavement deterioration modeling. And it's an error that is pretty common. And it happens when PCI in the subsequent year is larger than the current year, which is pretty uh, erroneous, right? So we expect PCI 2001 always be larger than PCI 2004, unless there's a maintenance or something happening in between, right? So the way to check this would be just simply manually going through all your data points, see where PCI is increasing. But in this case, it's only 99 road. Maybe you could do it, but in a lot of cases, it's very difficult because you have quite a lot of data, right? So um, you could either write a query like this and find your erroneous data. For example, here in these cases, PCI has increased, which is counterintuitive, right? So it's either a maintenance was occurred or it's the data is erroneous. In some cases, these two PCIs are pretty close. For example, this one is 76, 77. It could be simply a minor error of, for example, rounding numbers and things like that. Or this one is 98, almost 100. So they're pretty close. But in some cases, like 12 and 58, this is clearly an error, right? And defining what is error and what is not error, that itself is a pretty subtle area that you could have different functions, different methods to approach what is erroneous, what is not. So, so in the next step, you have to add your other features. So initially, what you had was you initially had PCI, and then you have to add age, and then you have to add precipitation, and you have to add traffic to make a good prediction, right? And this is not an SQL syntax. I'm just saying you have to add these other features. And adding all these features is going to be through these SQL join queries, right? Which is pretty time taking. So in my case, what I did was I automated all the queries using a code that I developed in Python. So that's almost it about retrieving and a little bit of preparing data using SQL. It's really much more than that. As I told you, I had to create all these views that you see on the left. So these are all views created by me, to analyze the deterioration of PCI in 3 years. So there's a lot of work in here, but when you get this part done, which is the retrieval and preparation of your data, you will be ready to train some model and conduct some real analysis on your data.